Okay, so please, Piotr.
So thank you very much for the invitation. That's a great honor for me to talk about my research. So I slightly changed the title of my talk. Now it's on the Gromov, the non-embedding theorem. So I'm going to present a new proof of the Gromov non-embedding theorem that I discovered with Armin Schikorra. So in '96, Gromov proved a result about non-existence of Hölder continuous embedding of Euclidean space into the Heisenberg group. So I'm going to talk about my new proof with Armin Schikorra. Actually, it's not that new. We had it for several years, but we wanted this to be a part of a larger paper, which is now 100+ pages. But then we decided just to publish this separately. So this will be a pretty technical talk because I want to show details of the proof. So even if you cannot follow all details, I hope you will see the overall idea. So that's the paper. It's now on arXiv and it's submitted. Okay, so Heisenberg group is a Lie group structure on R2n+1, and with such a group law. And as the Lie group, it has the basis of left invariant vector fields. So these are the left invariant vector fields, which at the origin are d over dxj, d over dyj, and d over dt. And in the Heisenberg group, we consider the so-called horizontal distribution, which is the span of the xj and yj vector fields, so 2n vector fields. We simply forget about the vector field d over dt. So the horizontal distribution is a 2n dimensional subbundle in the 2n+1 dimensional tangent bundle. So that's the horizontal distribution. And we equipped the Heisenberg group with the so-called Carnot-Karatodori, which measures distances between the points along the horizontal curves, which means the curves which are tangent to the horizontal distribution. I will provide more details later. So we are interested in the Heisenberg group as a metric space. We want to understand the properties of the Heisenberg group as a metric space. So for us, the group structure is less important, but it plays an important role in many proofs. And it turns out that this horizontal distribution is exactly the kernel of this standard contact form. So this is a one form on a 2n+1 dimensional tangent bundle. So the kernel will be 2n dimensional, and exactly the form vanishes on a vector if and only if the vector is in the horizontal distribution. So in other words, the horizontal distribution is nothing else but a standard contact structure on R2n+1. So we have two different names, but the same object. It depends on who's working on this problem, whether people are interested in the Heisenberg group or in contact geometry, but that's the same object. So horizontal curves are also called Legendrian curves, and the Heisenberg group is again equipped with the metric, Carnot-Karatodori metric, which measures distances between the points along curves which are tangent to the horizontal distribution. So such curves are also called horizontal. So more precisely, an absolutely continuous curve in R2n+1 is horizontal or Legendrian if the tangent vector it belongs to the horizontal distribution. And it turns out that any 2 points in the Heisenberg group can be connected by a horizontal curve, and we define the Carnot-Karatodori metric So the Carnot-Rotary distance between points P and Q is the infimum of lengths of horizontal curves connecting points P and Q, where the length is computed with respect to the left invariant metric, Riemannian metric on the Lie group. So how does the Carnot-Rotary metric compare to the Euclidean metric? So on every compact set, it is greater than or equal than the Euclidean distance up to some constant, but it's less than or equal than the square root of the Euclidean distance. That means the topology induced by the Carnot-Rotary metric is a standard Euclidean topology, but the metric properties are different. And in fact, the Carnot-Rotary metric is Euclidean in some directions, but purely fractal in some other directions. And the Hausdorff dimension of the Heisenberg group is 2n plus 2, while the topological dimension is 2n plus 1, because the Heisenberg group is homomorphic to R2n plus 1. That also shows that the Heisenberg group is non-smooth, and methods of differential geometry or smooth analysis cannot be directly applied to the Heisenberg group. So because of this non-smooth structure of the Heisenberg group, Gromov initiated the program of investigating properties of Hölder continuous mappings into the Heisenberg group, or more general mappings into sub-Riemannian manifolds. But today we will just focus on the Heisenberg group. So Gromov proved the following non-embedding result. If we have Hölder continuous embedding of the Euclidean space Rm into Hn, then m has to be, then a gamma has to be less than or equal than n plus 1 over n plus 2. So here the assumption that m is greater than or equal n plus 1 is important, because there are a lot of smooth horizontal surfaces of dimension n. So, but if we go from dimension n to dimension n plus 1, there are no longer smooth horizontal surfaces. And one can ask about the existence of Hölder continuous embeddings. And Gromov proved that actually the Hölder continuous exponent cannot be too large. He got this upper bound. So his proof was difficult, and I will show I believe elementary proof of a slightly more general result. So in the case when m equals 2 and n equals 1, so we are looking from mappings from R2 into H1, it follows from Gromov's theorem that gamma has to be less than or equal to 2/3. And actually, Roger Zust gave a very different proof that there's no, that if there's a Hölder continuous embedding of R2 into H1, then gamma has to be less than or equal to 2/3. But his proof was based on the factorization through certain topological trees, and this argument cannot be adapted to general case because this is a purely two-dimensional proof. So we gave a new proof of a slightly more general result, but before I will state and prove this result, let me comment on Gromov's theorem. Okay, so that's Gromov's theorem. And in particular, if you have a Hölder continuous embedding of R2, then gamma is less than or equal to 2/3. And Gromov conjectured a much stronger estimate that gamma is less than or equal to 1/2. Actually, when you have any smooth mapping from R2 into R3, then it's immediately 1/2 Hölder continuous as a mapping into the Heisenberg group, because the Carnot-Rotary metric, as we have seen, is bounded by square root of the Euclidean distance. But Gromov thought that that's actually the best possible situation. So Mira, Schikorra, and we ran numerical experiments which actually suggested that there is some possibility for the embedding when gamma, for any gamma less than 2/3. More precisely, we provided the numerical support for the fact that when you have a smooth horizontal mapping from the circle, then such a mapping admits gamma Hölder continuous extension. So we had some numerical evidence, but no proof. And recently, Wenger and Young, they proved that the pair R2H1 has the gamma extension property for any gamma between 0 and 2/3. And then in particular, if you have a Hölder continuous mapping from the circle into H1, that admits a C0 gamma extension to the entire disk. But their construction cannot lead to embedding because this is so-called Kaufman type construction, where open and dense set is contracted to the one-dimensional set.
So Piotr, this means that this Gromov conjecture is still open then?
I mean, for embedding, yes.
Mm-hmm.
For embedding, yes. But that would be very hard to prove if this is true. So, so that's our result. The statement looks kind of complicated, but I will try to explain. So again, so like in Gromov's theorem, we assume that M is greater than or equal n+1. And then we are looking at mappings from the ball into the Heisenberg group, which are gamma Hölder continuous as a mapping into Heisenberg group, and theta Hölder continuous as a mapping into Euclidean space. Okay, so we distinguish two different exponents of the Hölder continuity, and gamma is between 1/2, which everything is 1/2 Hölder continuous, up to n+1 over n+2, which is this exponent given in the Gromov's theorem, and theta is somehow expressed in terms of gamma. What is the meaning of the plus here? Because we have gamma plus and theta plus. So a function is C0 alpha plus if the constant in the Hölder inequality with exponent alpha goes to 0 when the distance between the points goes to 0, which means C0 alpha plus are functions which have a slightly better modulus of continuity than C0 alpha, but it is not really said how much better, just anything better than alpha Hölder continuity. Okay, so this is this theorem, but just stated in the more compact way. So if we have gamma and theta and the mapping in this class, which is gamma Hölder continuous into Hn and theta Hölder continuous into R to n+1, then there's no such a mapping which, when restricted to the boundary, would be an embedding. So Gromov talked about the embedding of Rm into the Heisenberg group. So in particular, when you restrict this embedding to the sphere, that would be embedding of the sphere. Okay. So when gamma equals n+1 over n+2, then theta is also equal n+1 over n+2. And as a corollary, we obtain the following result. If M is greater than or equal than n+1, then there is no mapping in this C0 n+1 over n+2 plus, such that the mapping restricted to the boundary would be a topological embedding. And that implies Gromov's theorem. It's a slightly better result because we're not talking about embedding, but the mappings such that the mapping restricted to the boundary is a topological embedding. So the mapping would somehow have to fill this n+1 dimensional hole. And instead of saying that gamma is less than or equal than the n+1 over n+2, we get that slightly better result, that you cannot have embedding in the n+1 over n+2 plus. But I believe that Gromov's arguments would also give this result. I have not checked this carefully because I don't understand Gromov's proof, but I think it follows from his proof. So that's
Piotr, Piotr, can we have a little discussion at this point?
Yes.
So, why is this not in contradiction with the result of Young and
Because because they
because
are
one can start with the topological embedding of the circle, and this would give an extension, but maybe would not have this plus. Is
yes,
that correct?
yes, and also they have extension for gamma strictly less than n+1 over n+2. So the case n+1 over n+2 is open. So like in the case of mappings from R2 into H1, there are extensions when gamma is less than 2/3. There are no extension when gamma is greater than or equal to 2/3 plus.
Okay.
But it is not known whether there is extension if you have 2/3.
Okay, but now I
So-
did not understand why your corollary gives Gromov theorem, because it could be that, you know, there is a map that is n+1 divided by n+2 Hölder, or
Yes, which means it follows from our corollary that if there is if there is an embedding, then gamma has to be less than or equal than n+1 over n+2. Has to be
right, because
strictly
if the
less than
Hölder
n+1
coefficient,
over n+2
right,
plus.
if the Hölder coefficient is strictly smaller than this 2/3, then the map would be in 2/3 plus.
Yes. Yes.
Okay.
Yes. Yes.
Thanks a lot. Thanks. Piotr.
Okay, so in particular, there's no mapping from the two-dimensional ball into H1 in the 2/3 plus case. However, the case whether there is such a mapping in C0 to thirds, that's open. So, and this result is sharp because Wenger and Young showed that if you have the extension, if you have such a mapping, I mean, they show that for any gamma less than 2/3, there is a Hölder continuous mapping from the two-dimensional disk into H1, which on the boundary is an embedding because you have the extension property. So this shows that it's sharp. But the case when you are looking at the mappings in the class C0 to thirds, this is the open case. So again, this is this result. But when we take theta equal 1/2, gamma equal 1/2, then theta equals 1 as a corollary, we obtain that there's no embedding of the m-dimensional ball with such that this is a Lipschitz continuous mapping into Euclidean space, but C0 1/2 plus mapping from the ball into HN. So let me remind that any Lipschitz continuous embedding into R to n+1 is automatically C0 1/2 embedding into the Heisenberg group. However, this result says that there is no such a mapping in the class C0 1/2 plus. And this result was actually proved by Balog, Wildring, and myself in 2014, but with a different method. So actually, the result that we proved with Armin Schikorra is a sort of interpolation between this result and Gromov's result, where we have this whole scales of Hölder continuous exponents in between. So that's the theorem. And let me sketch the proof. So first of all, if we have a mapping from the m-dimensional ball where m is greater than or equal than n+1, then you take a slice, n+1 dimensional slice, then you have a mapping from this n+1 dimensional ball. And if the original mapping was the embedding of the boundary, it will be embedding of the boundary of this n+1 dimensional ball. And because exponents gamma and theta, they don't depend on m, but only on n, it suffices to assume that m equals n+1. So that's a trivial reduction. We can assume that m equals n plus 1, and that means it suffices to prove this result. So that's the same result, but we are showing that there is no mapping from n plus 1 dimensional ball such that in one of those two classes, such that the mapping restricted to the boundary is a topological embedding. Okay, so that's the same theorem, but just squeezed to save space, and the idea of the proof. The idea actually that I'm going to present makes absolutely no sense, but the way it will be written. So suppose that such a mapping exists. What we want to do, we want to construct a closed form with compact support, n plus 1 form on R to n plus 1 with the support away from the image of the sphere, and such that the pullback of the form by the mapping equals 1. That doesn't make sense because the mapping is Hölder continuous. So what does it even mean, the pullback of the form? Second, we would like to show that the rank of the derivative of the map is less than or equal n. Again, it doesn't make sense because this is Hölder continuous map. It's not differentiable. But if we somehow could prove this, then we would arrive to a contradiction, because on the one hand side, the integral of the pullback of the form is 1, but if the rank of the derivative is less than or equal n, then the pullback of n plus 1 form is 0. So the integral would have to be 0. We arrive to contradiction. So this argument works if f is Lipschitz, because it's known that every Lipschitz mapping into the Heisenberg group has a rank of the derivative less than or equal n. That's a very standard result, well known. And we could apply this argument to the Lipschitz mappings. But the point is that we want to go beyond Lipschitz class and prove this result in the Hölder continuous case. So by this argument, we would see that there's no Lipschitz mapping of this property, but that can be proved by easier arguments. Okay. So how to deal with the Hölder continuous mapping? So we have to discuss the pullback of the form in some distributional sense and the rank of the derivative in the distributional sense. And we can do this, define the pullback of the form and rank of the derivative in the distributional sense by looking at smooth approximations of the mapping and see what happens when you pass the limit with the smooth approximations. But one has to be very careful. Okay, so that's the lemma. If we have a topological embedding, so this has nothing to do with the Heisenberg group. Any topological embedding of the sphere into R2 n plus 1, then there is a closed form, compactly supported n plus 1 form with support away from the embedded sphere, such that when you look at a sequence of smooth mappings, which when restricted to the sphere will converge uniformly to F, then the integrals over the ball of the pullbacks of the form equal 1. Okay, so this will be a kind of a replacement for this condition that integral of the pullback is 1. Because if we approximate smoothly the mapping by whatever smooth approximation, say by convolution, then eventually this integral will be 1. Why is it true? So let me draw a picture. Let me draw a picture. Why is it true? So if we have a sphere Sn and we have embedding F, so this is embedded sphere. So this is F of Sn, and this is in R to n plus 1, and assume that this is a nice embedding. Okay, assume this is a nice embedding. Then you can find a circle like homomorphic to Sn, which is linked with this. Like this is n-dimensional circle, this is n-dimensional circle. The sum of the dimensions is 2n, so they are linked in R2 n plus 1. Well, now you replace this sphere by a torus, and then in the slices here have dimension n+1. And what you do, you build a form with support like this. So this is like a form which is in each of those slices, and in some kind of counterpart, you do it in the counterpart of like spherical coordinates, but not spherical, but toroidal coordinates, whatever it means. Okay, so you can, so this form kappa will be n+1 form because it lives on n+1 dimensional slice, and we'll have a compact support away from the embedded sphere. And now, when you do the approximation, f epsilon, so you do the approximation such that image of the sphere is very close to the image of the sphere. The pullback of this form, if everything should look nice, will look like this. Will be just one bump. So the integral of the pullback on the ball will be 1. So that's the idea, but this idea doesn't work, because in general you cannot link the embedded sphere with another sphere. In general, there are counterexamples. You can have a circle in S5 which cannot be linked with any three-dimensional sphere because the complement has third homotopy group 0. So in general, it doesn't work, but it works at the homology level. And actually, what you can do, you can prove the existence of some form using, using Poincare and Alexander dualities, or you can mimic those proofs, the construction of the Meyer-Vietory sequence, and this is what we do in the paper. So we construct this form explicitly by just mimicking the construction of the Meyer-Vietory sequence. So the construction is elementary, it doesn't require any knowledge in algebraic topology. Anyway, such a form exists. And now, if we could approximate f smoothed by horizontal maps, f epsilon, then for horizontal maps, the rank of the derivative would be less than or equal n, and the corresponding integrals would be 0, and we will arrive to a contradiction. Well, but this way, that simply means that the mapping f, if this cannot be approximated by horizontal maps f epsilon. So that's not much. But because unfortunately, if you do the approximation, say by convolution, the approximating mapping of epsilon will never be horizontal. It simply cannot be horizontal. So it doesn't work. So one has to study this approximation very carefully. Okay. So this is a standard for modifier, and we will do a brutal approximation by convolution, nothing sophisticated. So derivative of this convolution approximation is given by this formula. Now observe that integral of dphi over the ball is 0. So therefore you can subtract a constant and nothing will change. So this integral equals to that integral. So this is what the original, I'm subtracting the constant because I'm integrating with respect to z. So this is equal. This integral equals to that. Okay, and now if I define as this semi-norm f to be the Hölder, the constant in the Hölder's inequality, then this estimate gives this immediately, because you estimate f of x minus z minus f of x by using Hölder inequality. So this is like a Hölder constant of f, and because the distance between x and x minus z is no more than epsilon, you will have epsilon here to minus m minus 1 times volume of the ball, and here will be epsilon to gamma, and will give you epsilon to gamma minus 1. So that's a very, very simple estimate. Okay, very simple estimate. Now, when you want to observe that if f is in C0 gamma plus, then this semi-norm, because I'm looking here at evaluate this when the distance is less than epsilon, will converge to 0 when epsilon converges to 0. Okay, because this is the semi-norm when I take the supremum over points with distance less than or equal epsilon. So that's an important observation. And now we have, as a corollary, we have such a lemma that when you have Hölder continuous mapping into the Euclidean space and you take any K form, then the pullback of the K form is bounded by this. Why? Because when you take the pullback of the K form, then this is a linear combination of K-fold products of derivatives. For each derivative, you get this estimate, so you take it to the power K. And this is you multiply by the supremum norm of the form, just the coefficient in the form. So that's a trivial estimate. Look, this estimate does not depend on the dimension D. Maybe constant will depend, but the important part will not depend. So in particular, I have the same estimate for when you have a mapping into R2 plus 1. So I'm copy and paste the statement. But now, look, if I have a Hölder continuous mapping into the Heisenberg group, then it is a Hölder continuous mapping into Euclidean space, because identity mapping from the Heisenberg group to Euclidean space is locally Lipschitz continuous. So if I have a Hölder continuous mapping into the Heisenberg group, I get the same estimate because such a mapping is Hölder continuous into Euclidean space. So if I have a Hölder continuous mapping into the Heisenberg group, I have the same estimate. That's trivial. But that's a bad estimate because in general, it will blow up when epsilon goes to 0 because the exponent is negative. But it turns out that in the case of the pullback of the contact form that I discussed before, you get much better estimate because the exponent is different. And observe that in particular, if f is in C0 1/2 plus, then the exponent is 0, but the semi-norm of f will go to 0. So that goes, the right-hand side goes to 0. If I look at the first estimate, it will blow up. It will blow up, but this is a better estimate. So the first lemma was trivial. The second one is less trivial. So how to prove it? So we define for points P and Q. So X is in Rn, Y is in Rn, and T is R. We define this kind of expression. And it is easy to see that this expression is bounded by the Kano-Karato-Dori distance squared. Why? Because Kano-Karato-Dori distance is equivalent to the so-called Korani distance. And this expression APQ is just a part of the Korani distance. So it appears explicitly in the Korani distance. So this estimate follows directly from the fact that the Korani distance is less than or equal than the Kano-Karato-Dori distance because the two distances are Lipschitz equivalent. But observe that this expression A is somehow similar, at least formally similar to the contact form. There is some similarity. And because of that, if you do the elementary algebraic calculations, you see the following, that if you have a mapping into the Heisenberg group and you brutally approximate this by convolution, then the pullback contact form is expressed in this way that you can write it in terms of A. You just take the pullback of the form, you write it down, and it's just 3 lines of algebraic calculations to get this formula. It's very easy. So you just estimate absolute value in this way. Now you estimate A, absolute value of A by Kano-Karato-Dori distance squared. And now, if you know that, so so this is the estimate, they just copy and paste. If you know that the mapping is Hölder continuous into the Heisenberg group, then you can express this Kano-Karato-Dori distance squared by 2 epsilon, because the distance between P minus Z and P minus W is at most 2 epsilon. So it will be 2 epsilon to the power gamma. And then if you estimate the integrals in the standard way, you exactly get this estimate. So that's a simple algebraic computation, a little bit tricky, but this is elementary. Okay, so we have this lemma. So because we have such an estimate, okay, because the distance between P minus Z and P minus W is at most 2 epsilon. So when you plug it here, you get this estimate. So what we have this estimate for any K form, which is bad because it blows up when epsilon goes to 0. And we have this good estimate when we have a contact form. Now, suppose that we have a form kappa, which can be represented as the wedge product of the contact form and tau. Then for such a form, we can get a better estimate than the estimate from the first lemma, because we can apply the first lemma to estimate tau, and the second lemma to estimate alpha. So if we know that kappa is a product of alpha and tau, we can get a better estimate than the estimate coming from the first lemma. Not as good as the estimate coming from the second lemma, but better than the one from the first lemma.
So Piotr, sorry, I'm confused by one point here. You're saying, you know, the second lemma is better than the first lemma. So why do we talk about the first lemma at all?
Yeah, because in general, there are forms which are not contact forms. And we want
I see. So the word contact is important in
yes,
the second.
It's only for the contact. It's only for
okay.
contact.
All right.
Alpha is a contact form. Okay. And this is where we need the Lefschetz lemma. So the Lefschetz lemma says that the exterior product with with symplectic form is an isomorphism from n-1 forms onto n+1 form. So every n+1 form can be written uniquely as a wedge product of omega of the symplectic form and n-1 form. That's a beautiful lemma, but this is just linear algebra. And if you try to do it by hand, that you will immediately get lost with computations. And there is a beautiful and quite unknown proof due to Calabi, which is just published in one book by Robert Bryan. Okay, so that's the lemma. And now when we have contact form, the exterior derivative of the form is more or less symplectic form. It's not exactly the symplectic form, because symplectic form lives on R2n, and this form lives on R2n+1. Okay, so this is like a pullback of the symplectic form when you have a projection from R2n+1 onto R2n. Anyway, the Lefschetz lemma and this fact that the alpha is a symplectic form gives the following result: that when you have any n+1 form on R2n+1, then you can decompose this form as the wedge product with the contact form plus wedge product with the alpha. How to do this? It's very simple, because when you have when you have n+1 forms, it has terms that have dt and terms that do not have dt. You can collect all terms that have dt in alpha wedge dt, d beta. Then when you have alpha wedge d beta, when you have kappa minus alpha wedge d beta, you will only have terms which do not have dt. And because of the Lefschetz lemma, every form which depends on xj and yj can be written as the wedge product. So the alpha is essentially the symplectic form that can be written as a wedge product. And moreover, it is important that if the supports of the form beta and delta is not bigger than the support of kappa. That follows from the construction. So this is the lemma, that every n+1 form can be written that way. And now let me, so this is this topological lemma that I mentioned before, that when you have a mapping from topological embedding of the sphere, then you can find n+1 form with the compact support away from the embedded sphere, such that for any smooth approximation, the pullback will be eventually equal 1. And what we do, you can write kappa as alpha wedge beta plus d alpha wedge delta. You can write it. Okay. So when you write this, you can write kappa as alpha wedge beta plus d alpha wedge delta. And because the support of beta and delta is not bigger than kappa, if the kappa had compact support in this set, beta and delta will have compact support in this set. So we write kappa as alpha wedge beta plus d alpha wedge delta, and then pullback of kappa will be equal to that. What we do, we can now here perform integration by parts. Because of the compact support, we can move d from here to there. So that's what we do. Okay, so that was before integration by parts, and after integration by parts, d moves to d delta. Now I have f star alpha and I have f star alpha. So I can write that this is f star alpha wedge f star of beta plus d delta. So that's what I do. So that's the same expression. Okay, so what we have, okay, so this is what we have. Now let's recall. We have this bed estimate when you have a Hölder continuous mapping into R2 n+1. Then for n form, you have such bed estimate. So this is the estimate I didn't like. And for contact form, we have a good estimate. And now, when I have a mapping which is Hölder continuous, gamma Hölder continuous as a mapping into the Heisenberg group, and theta Hölder continuous into Euclidean space, then I have a good estimate for the pullback of alpha form that comes from this gamma Hölder continuity, and bad estimate for pullback of theta, where theta is n form. Okay, so let me copy and so that's a theorem we wanted to prove. And suppose that such f exists. Then let's recall when I have n form that I'm just copying this statement. I'm just copying the corollary. Because f is gamma to hn, theta to rn+1, and we have some estimate. Now, f is gamma to hn and theta to r2n+1, so we have such estimates. So this is a copy and paste from the corollary. So good estimate for the contact form, bad estimate for generic form. And this is the lemma that we proved. Right? Let me recall. So this is the lemma that we proved, that we could construct forms alpha. So alpha was a contact form, but beta was n form and delta was n-1 form, so that this integral is 1. So I copy and paste. Now observe that beta plus d delta is an n form. So I can use this f star tau estimate to estimate f star beta plus d delta, and I can use f star alpha, estimate f star alpha using the first estimate. So what we get, when I put absolute value, 1 will be less than or equal than norm of f star alpha. I just copy and paste this estimate, and norm of f star beta d delta, so I copied this estimate. Now, because gamma and theta are connected through this equation, that theta equals n+1 over n-2 gamma over n, it turns out that exponents 2 gamma minus 1 and plus n times theta minus 1, they add up to 0. So they are gone. So we get that this is just a gamma norm squared of f and theta norm to the power n. And that converges to 0. Why? Because f belongs to C0 gamma intersected with C0 theta, so which means both expressions are bounded. However, f is in C0 gamma plus or f is in C0 theta plus. If f is in C0 plus, then the first factor converges to 0. If f is in C0 theta plus, the second factor converges to 0. So the product converges to 0, and we arrive contradiction, and that's the end of the proof. Okay, that I want to stop now.
Okay, thank you very much. So comments or questions? So it seems that in the argument there's very little room for improvement, right? I mean, it's a pretty sharp proof in a sense.
Yes.
Right. I mean, in some sense, everything depended on this trick that you bring in the contact form.
Yes.
Right. And that for the contact form you have this better estimate.
Yes. Yeah, so there is very little place.
Can you say it again? So now beta plus d delta, these are very specific forms, right?
Yes.
These were coming from decomposing the formula you got from the Lefschetz, no, from
no,
duality,
let me
correct?
go back here. So we have this lemma. So this is basically Alexander duality.
Yeah, the Alexander duality. Yeah.
Expressed in the theorem cohomology.
Mm-hmm.
So, and now what I do, kappa is the n+1 form. So what I do, I decompose this form kappa as alpha wedge beta plus d alpha wedge delta.
Mm-hmm. Yeah, but
then,
what I'm saying that okay, you have this integral, and then okay, you prove that on the one hand goes to 0, but on the other hand is constantly equal to 1, contradiction. Yes. But it seems that therefore every such an f, which of course it doesn't really exist at the end, but has at least one of this form k attached in some way, and so
this form kappa is basically the form which observes the whole. When you have the embedded sphere, the cohomology of the complement, n+1 cohomology is Z or R, if you look at the theorem cohomology. So this is the form which generates this. So
well, I guess the trick then is, you get this form out of general considerations, and then the trick is to use your algebraic lemma, right? I mean, that you are able to somehow write this form where you see the alpha appearing.
Yes. So somehow we'll have good estimate for the contact form, bad estimate for any other form. So when you have n+1 form, you want to benefit from having a good estimate for the contact form. So you express this form in terms of the contact form.
But if instead now instead of the Heisenberg group you have some other group or some other subreal,
that's a very good question. That's a very
good
question.
At least a candidate for the K?
I don't.
Homology.
I mean,
so Enrico, sorry, Enrico, say this again. What did you say?
So now, if instead of having as a target the Heisenberg group, we have some other group, Lie group, Carnot group, or even a manifold. I was wondering if these cohomology arguments were leading to the existence of some form K.
For kappa will exist. This is not a problem. The problem is that I don't know what will be the counterpart of the Lefschetz lemma, because the contact form is a very specific form. So you would for this argument to work, you would need to have a counterpart of the Lefschetz lemma, so that this horizontal distribution would be generated by some contact forms, and any form in the suitable dimension could be represented in terms of the wedge product with those forms. That I don't know for what groups it would work.
I mean, of course, like now in other groups, we have this terminology, Michel Roumain complexes.
Yes, yes,
and
yes.
So what you're
I
saying
think,
is that something K represents something in that complex, probably.
yes, I think that the Roman complex would be the good replacement, but I'm not really well familiar with this.